to the Unit Operations Virtual Laboratory with Dr. Sandy Pettit. Today, we will be discussing the vapor-liquid equilibrium of the binary system composed of water and ethanol. In this video, we will be discussing the thermodynamics of phase equilibrium, the apparatus used to perform an isochoric and isothermal experiment, safety precautions, and tips for successful performance of the experiment. Before we dive into the specifics of this lab, let's consider thermodynamic equilibria from its simplest form in Raoult's law to more advanced equations that account for non-idealities. Thermodynamic equilibria between two phases is attained when the fugacities of the components in both phases are equal. The simplest form of this equality is Raoult's law, which assumes ideal behavior in both the gas and liquid phases. Mathematically, this is expressed as the species partial pressure equaling the species vapor pressure multiplied by the mole fraction. Graphically, the red dashed line shows the partial pressure of species A as its mole fraction increases. When a second species is added to the figure, the x-axis direction is reversed. The mole fraction of species B decreases when moving from left to right. Species B is represented by the dotted blue line. In an ideal solution, the summation of the fractional vapor pressure terms equal the vapor pressure of the solution. The solid green line shows this summation. At low pressures, the gas tends to behave ideally. However, the intermolecular forces in the liquid phase will result in non-ideal liquid behavior. This may cause a positive or negative deviation. In a negative deviation, the actual pressure of the solution is less than that predicted by the ideal Raoult's law calculation. The deviation can be predicted by modifying Raoult's law with an activity coefficient. An ideal solution would have an activity coefficient equal to 1. Coefficients are determined for each species and depend upon the other species in solution. They are predicted using empirical models such as Margulis, Van Laar, Wilson, and many others. Accuracy of the empirical models vary with the solution properties. Therefore, an appropriate model should be determined based upon the specific mixture of interest. Now let us consider the apparatus used to perform this thermodynamic study. The assembly is comprised of a sealed Erlenmeyer flask placed inside a water bath on top of a magnetic stir plate. The flask cap has connections for a pressure sensor, thermocouple, and 2 chemical port valves. The pressure sensor and the water bath thermistor are vernier devices which connect to a data acquisition system. For more information about their accuracy, please visit the manufacturer's website. The thermocouple, which records mixture temperature, is connected to a Barnard display and has a resolution of 0.1 degrees Celsius. Nitrogen is used to dry the vessel assembly and provides an inert environment for performance of the experiment. It is supplied from a compressed gas cylinder connected to a tank pressure regulator. The pressure is further reduced with a step-down regulator. When using the gas cylinder, identify the handles for the primary and secondary shutoff and the pressure regulator. Shutoff valve should only be used to open and close the gas source, not to regulate pressure or flow. The regulator should only be used to step down the cylinder pressure to the required system pressure. Never use the regulator to completely shut off flow. Improper use of these devices can cause internal damage and result in valve failure. Safety considerations for this experiment include chemical exposure to ethanol and nitrogen, and safe handling of compressed gas cylinders and sharps. Viewers should direct their attention to the separate video on general gas cylinder safety. Heating of cylinders may cause rupture, and rapid release of nitrogen may cause asphyxiation. When assembling the vessel, note that the needles which connect to the ports are sharp and can puncture the skin. Puncture wounds may lead to tetanus for individuals that have not been vaccinated. Reference the ethanol safety data sheet for more information on the specific hazards of flammability and toxicity. Nitrile gloves and goggles are required when handling ethanol to limit exposure. Transferring and pouring should be performed in the fume hood. To conduct this experiment, follow the steps as outlined in the lab guide. First, the system needs to be assembled from clean and dry parts. Remember to place the stir bar before sealing the vessel with the rubber stopper. Special care should be taken when handling the rubber stopper assembly due to the sharp needles. A weighted ring is used to stabilize the flask when it is placed in the water bath. Place it before connecting measurement devices and tubing. The orange threaded retaining ring is placed over the rubber stopper assembly and used to ensure a tight seal for the flask. To connect the chemical port valves, secure the needle fitting with needle nose pliers and twist the valve into place. Do not put tension or torque on the needle. They will snap and pose a further puncture hazard. Connect the pressure sensor and thermocouple to the flask assembly and place the assembly and the thermistor in the water bath. Open the valves and flush the system with dry nitrogen to create an inert environment for your experiment. Remember that your binary system is ethanol and water. Any residual water vapor from air will have a significant negative impact on your data collection. Perform a pressure test as directed in the lab guide. To begin your trial, check your flask pressure and temperature. The starting system pressure should be approximately atmospheric. You may need to vent your system. Fill 2 syringes with 10 cc's of liquid, one containing water and the other ethanol. Connect them to the chemical port valves. Begin by injecting all 10 cc's of water. Since this experiment is to be an isothermal and isochoric study, an equivalent volume to the volume injected must be removed. Retract the plunger, drawing in primarily nitrogen gas. Be sure to close the connection port valve after injection. Pressure buildup in the system could cause the plunger to be pushed out of the casing. Once the temperature and pressure stabilize, record this value. The increase in system pressure should be equivalent to the vapor pressure of the pure component at the system temperature. You will proceed with your experiment by injecting approximately 1 cc increments of ethanol, letting the system stabilize in between each injection. As before, an equivalent volume must be removed by retracting the plunger. Record the amount of ethanol injected at each step. As can be seen in the sample output from the data acquisition system, pressure rises when the sample is injected, drops slightly as the volume is corrected, and then stabilizes. Once stabilized, record the system temperature and pressure. Also, check and record the water bath temperature to ensure that the readings are being taken at isothermal conditions. Based upon the data collected in this experiment, you should be able to compare the experimental data with empirical predictions using the Van Laar activity coefficient, describe the phase equilibrium of the ethanol water system via XY and PXY diagrams, and compare this system to an ideal solution by evaluating the existence of an azeotrope and deviations from Raoult's law. Thank you for watching. This video has been produced in cooperation with the Chemical Engineering Department of the University of South Florida.